So I'm just going to change now for the second half of this lecture to do something more on PowerPoint, because I think this second half is perhaps more amenable to PowerPoint. It's less analytic than the first half, and perhaps more visual. And so where we've just got to, we've looked at the idea that gravitational waves create minute changes in the distances between 2 points, and that those are detectable potentially. We've looked at the sources that might come up and create those gravitational waves, and seen that binary stars, and in particular binary stars with relatively heavy component masses and small separations, are the prime source. And what that means is binaries containing neutron stars and black holes. It's also the case that gravitational waves carry energy and angular momentum that is removed from the binary orbit, causing the orbit to shrink until it merges. And clearly binaries are at their highest orbital frequency, and therefore the strongest gravitational waves, just before merger. So the best place to look for gravitational waves is in the merger of two binaries. And the merger time is a very sensitive function of several parameters. The Q key parameters are the separation and the masses of the components. And so you can see here, this is all expressed in solar units. So R with the dot here is solar radii, this is solar masses. And so 10 to the 8 years for a system with a solar radius separation and of order solar mass components. And there are very strong dependencies here, because you see that roughly speaking this is dependent on the fourth power of separation and the inverse of the cube of the masses, roughly. And so things that are substantially further apart or substantially less massive will take much longer to merge. And this is actually, this is an analytic result. Which is slightly different if you have eccentricity, but only slightly. And so the crucial point is that in order to have systems which will merge in a Hubble time, and a Hubble time is of order 10 to the 10 years, the age of the universe, you have to have separations for, say, 10 solar mass material of no more than a few solar radii. And that's kind of hard. So, there's an astrophysics lesson here, and this is not a course about stellar or binary evolution, so I'm not going to go through any of this in detail, aside from noting that although relativity is extremely mathematically difficult and complex, it's also quite precise. So this step where you have the duration of the min spiral is quite certain, whereas the steps beforehand are quite uncertain. And I'm not going to go through this in detail, but then there are many ways you could do this. But the basic principle is that I start with two stars which will create black holes or neutron stars. They are stars which are at least of order 10 times the mass of the Sun. The mass to radius relationship for main sequence normal stars is roughly linear. So something which is 10 times the mass of the Sun is also about 10 times the radius of the Sun. And these two stars, of course, can't touch. And so if you have a binary that contains two massive stars, it is much, much wider than the few solar radii that you need to have for gravitational waves to make your merger happen. And so you need to do something to take it from separations which are perhaps more like astronomical units, the distance between the Sun and the Earth, down to solar radii. And there's lots of complicated binary evolution that goes on in here, but the critical point is that at the end you have to go through this penultimate point where you have what's called a common envelope, where both stars orbit within the envelope, the atmosphere of one. That creates a lot of friction and it shrinks down your orbit, so you can end up creating a system with neutron stars or black holes with a separation of a few solar radii at most that will merge over the course of the age of the universe. And then you have to ask yourself, well, we've got these sources that may be detectable. How do we detect them? Well, these are creating the gravitational waves. These are minute changes in the relative path lengths, or the relative distance between 2 points. So if you imagine you have some set of free test masses that are arranged in a circle, as the gravitational waves pass through them, they will oscillate, the distances between them will change in the two polarizations, the plus and the cross polarization. If I use an interferometer, or I measure two orthogonal routes, I can see that at the beginning of this, for example, I'll measure the same distance, then I'll measure one longer, one shorter, then the opposite is true, and so forth. And so the idea of a gravitational wave detector is that what it does is it is a Michelson-Morley interferometer with various highly effective tweaks. But this is basically the same setup that was used by Michelson and Morley more than 100 years ago to measure the speed of light and show it was the same in every direction, therefore debunking the luminiferous ether and really giving some of the inspiration for the special theory of relativity. And so the idea is simple. You take a light source. Michelson and Morley had to use normal light, white light if you like. It's very complicated to do it like that, but it is possible. And these days we use lasers. This is a 20-watt laser that's operating in the LIGO detectors. This is the diagram of the LIGO detectors. You use a 20-watt laser. You fire that in, you split the beam, you send it down where it bounces between these two test masses in each orthogonal beam. And it bounces a few thousand times back and forwards between these test masses, and that gives you 100 kilowatts of circulating power. And as it bounces here, it's basically measuring a path length which is now something like 20,000 kilometers long. Bounces back, eventually comes back out, goes back to the beam splitter here, and gets recombined. And at this point, you still have monochromatic laser light. And what you can do is you can measure, or you can destructively interfere that light. So you basically tune the distances such that the two beams of light destructively interfere. That is that when you have a photodetector sitting at the bottom here, no light is in fact transmitted to that in a steady state. So when this is set up and there are no gravitational waves, there is no light on the photodetector. And then as gravitational waves move through, they make one arm slightly longer than the other by a tiny fraction, and they bring that cancellation ever so slightly out of phase, right? It's not even a tiny fraction of a wavelength, but nonetheless they bring it slightly out of phase. And so what you can do here is you then measure little flashes of photons in the photodetector, you measure their pattern, and that tells you something about the oscillation of the wave which is coming through you. This is a very difficult problem, and so this is what's called the sensitivity curve. It's basically characterized by the noise at a given frequency. Remember, this frequency is the frequency of the gravitational waves, or twice the orbital frequency. And you can see it's got a sort of curve in it. It's most sensitive here at a few hundred hertz. It's well below that canonical 10 to the minus 21, 1 part in 10 to the 21 variation that we need to detect astronomical objects. At the low frequency end here, this is actually dominated by seismic noise. That's very hard to get rid of. So these test masses are very isolated, so they're on quadruple pendulums. They're on platforms which are like noise-cancelling headphones and take out ground motion. But you still can't get rid of all of it, so there is a seismic noise floor at low frequencies. At high frequencies, you simply have the problem that you're sampling the laser very, very frequently, every 1,000 times or more a second, and you run out of photons. So you're shot noise or Poisson noise limited at the high frequency end. And what happens, and very conveniently, given this is just a fluke in a sense, that this is where the sensitivity is optimal, is that binaries, of course, enter at low frequency, they get closer and closer and closer until they merge, and then they stop emitting gravitational waves. And it turns out that many black holes and neutron stars merge in the sweet spot for the detectors here, according to our predictions. And so these are the gravitational wave detectors. There are currently 3 of them that are in reasonably good operations. This is LIGO Hanford in Washington State, LIGO Livingston in Louisiana, and Virgo in Pisa in Italy. LIGO and Hanford have 4-kilometer arms, Virgo has 3-kilometer arms, and these are 3 detectors. The idea of having 3 detectors is twofold. It's firstly that any local noise can get removed. So, for example, there's lots of logging that goes on around some of the LIGO detectors. You don't want a tree falling to confuse that for a gravitational wave signal, and therefore you have to see the detectors in multiple signals in multiple detectors to be sure. Secondly, there is a light travel time from A to B to C, and so where on the sky your source is depends on the delays of detection between these different detectors, while the polarizations, because of the different orientations of the detectors on a globe, for example, gives you some information about the polarization. And so with all of that information, you can reconstruct the positions of sources on the sky, as well as being confident about detection. And this is the first detection, and it's a remarkable thing because it is a detection which you could actually see with the naked eye. So this is the strain measured as a function of time at the Hanford detector and at the Livingston detector. And the other one is inverted because that's how you have to actually match them up because of the orientation of the detector, etc. And you have to shift them in order to match up the time lags. But you see in two detectors, you basically see exactly the same signal with the same amplitude and the same frequency evolution. And in the middle panel, you see the simulations that come out of numerical relativity. So this, remember, is a potentially two spinning black holes, which are going through a dynamic merger. So you have complicated metrics to worry about because you have more than one source of mass. You don't have spherical symmetry. You don't have time independence. You have angular momentum. So it's a very complicated thing. There isn't an easy analytical solution. So you solve this via numerical relativity. And what you actually do is you have a set of template banks which have a range of masses, spins, etc. in, and you compare these with your real data in more or less real time. And these are then, more refined templates, but they very well match the signals you see in Hanford and in Livingston. And then this is the residuals when you take the model away from the data and you see they're very small. You've got a good description of your data. And what you're seeing here is you're seeing basically an increase in the frequency and an increase in the amplitude until the merger, and then there's a little bit afterwards, it's called the ring down, and then there's nothing. And the very bottom panels here show what's called the chirp signal. So gravitational waves emit a chirp. That is an increase in frequency and amplitude with time. So, sometimes you'll see people play these and they go, whoop. That is the noise a gravitational wave makes. It's actually a real audible frequency, right? A few hundred hertz is a frequency that we can hear. So people often talk about gravitational waves as being a way to listen to the universe. So this is the actual chirp signal. And this is the first detection. This is from September 2015. These signatures, you get the numerical relativity output. That's a very precise measurement of the properties of the binary. And this is a black hole binary with two components about 30 times the mass of the sun. And a total mass, therefore, when you merge, of about 60 solar masses. It's actually a little bit less than the mass of the two because you've actually radiated several solar masses of energy using E equals mc squared in gravitational wave energy. And unsurprisingly, if you make this sort of discovery, you win the Nobel Prize. So this is Rainer Weiss, Barry Barish, and Kip Thorne, who won the Nobel Prize for basically their work on LIGO over the course of 50 years. And, unsurprisingly, they're now the representatives of a 1,000-strong collaboration. This is a very big, ongoing project, but it's really quite a significant piece of work. And indeed, if you were there at the beginning 50 years ago, then you win a Nobel Prize very deservingly when you actually finally discover gravitational waves. And there have been many gravitational wave detections since, most of which have come from binary black holes. And so this diagram shows you on the y-axis the total mass, and on the x-axis is just sort of arbitrary to put things on. And so the purple points here are EM black holes. That is black holes that have been discovered in binary star systems where we've measured the orbit and got the black hole mass out. At the bottom we have the neutron stars, and I'll come and talk about that later. And then at the top you have the LIGO black holes, and of course every time LIGO sees a merger, it actually sees three black holes. It sees the two that go into it, a merge, and the one that results at the end. So you get a new mass distribution for black holes. And you'll notice that they're all much more massive. Some of these are peaking up over 80 solar masses combined mass, much heavier, 4 times or more massive than the systems we discover in EM light. That is not, in fact, surprising, because if you think back to the last bit that I wrote, the gravitational wave sensitivity is essentially dependent on the mass. And so the strain is larger in more massive systems. And because the strain only falls off linearly with the distance, you actually have a much bigger impact of larger mass systems observationally. So when you look with LIGO and you look at a system of a population of black holes, you preferentially find ones that are more massive rather than less massive. Although that statement does rely a little bit on what the underlying population is, because clearly there need to be massive black holes there. But nonetheless, that's giving you a very new view on all of these black holes. And then the last thing that I want to talk about today is, in fact, how gravitational waves pair with electromagnetic light. And to do that, we need to worry not about the black holes. Black holes don't emit light unless there's other material around them. We instead need to worry about the neutron stars, and that's what I'll talk about next.